So in this related rates problem, we read that the pH of a solution is given by, okay, pH is equal to negative log of the hydrogen ion concentration. Okay, so that's what that all means there. And you're familiar with that. You've seen that before. If, due to titration, the pH of a solution decreases at a rate of 0.5 per minute, how fast is the hydrogen ion concentration changing when the pH is 5? Okay, so what do we know? Well, we know that the pH is equal to the negative log of the hydrogen ion concentration. And again, I identify that because you might not know that off the top of your head. If you've taken chemistry, you've seen that before. And you've probably seen this in another course, actually, even another math course, when you talk specifically about logarithms, because that shows up quite a bit. We know that the rate at which the pH is changing, okay, it's decreasing, so it's going to be negative 0.7 per minute. Okay, and what we want here is how fast the hydrogen ion concentration is changing. This is what we want to know here, and we're given again a little bit more information. We know specifically that the pH that we're looking for here is going to be 5. We want to know how fast it's changing at the instant that it's 5 here. All right, well, let's jump in. So here we go. pH is equal to the negative log of the hydrogen ion concentration. Now the wonderful thing about this equation is it's just those two variables there. So we can just jump in and take the derivative. So the derivative of the pH is going to be negative, okay? Now the log of that was going to be 1 over the hydrogen ion concentration, and we have to multiply by the natural log of the base, which will be 10. So natural log of 10. And then this will be multiplied by the derivative of the hydrogen ion concentration. Okay, so now I am looking for the rate at which the hydrogen ion concentration is changing. So I'm going to bring that over here because most of us like to have that on the left. That is going to equal, I'm going to bring the negative over and bring this stuff up. So this is going to be the negative hydrogen ion concentration. That'll be the natural log of 10, and then we'll multiply this by the rate at which the pH is changing. Okay, now let's take a quick look here. What do we got? I just got to plug this in now. So, okay, right off the bat, I don't know what the hydrogen ion concentration is at that moment. I do know that I'm interested in it when the pH is 5. So I'm going to go back to my pH equation. So the negative log of the hydrogen ion concentration, I'm going to make that 5. Bring the negative over. And then when I convert this, will be 10 to the negative 5 is equal to the hydrogen ion concentration. Now, I just need that value. I'm not going to put that in terms of, like, let's say moles per liter or whatever. I just need a value for that, okay? And it can be in whatever form I need it to be in. I'll take that and bring that here. So this will now be negative 10 to the negative 5 times the natural log of 10. And then we got the rate of change of the pH, and we knew that that was negative 0.7. Okay, so now let's put that all together. So this is going to be negative 10 to the negative 5. We're going to multiply that by the natural log of 10. And we're going to multiply that by negative 0.7. And what I get here is 1.6, let's say 1 to the nearest hundredth, times 10 to the negative 5. Now this is going to end up being moles per liter, because that's how chem people like to talk about it. Anyway, there you go. Now notice that this is increasing. This is positive. The hydrogen ion concentration is increasing. Now, if you're a chemistry person, that makes perfect sense to you. But if you're not kind of a chemistry sort of person, this might be confusing because we were talking about pH decreasing. As pH decreases, as something gets more acidic, the hydrogen ion concentration goes up. So that's actually exactly what I would have expected. So that's perfect.